All right, so maybe we can begin. The first speaker of today is Shota Komatsu, and he'll tell us about Coulomb branch of n=4 super mills and integrability.
All right, thank you, Sylvia, for introduction. So yes, by the way, can you hear me? I guess the microphone is working, right? All right, so the Coulomb branch. So I'm going to talk about the Coulomb branch of n=4 super mills and then its relation to integrability. I'm going to explain why this might be of interest to this audience. So I'm mainly talking about this paper that we put out this May, which I wrote together with Ivanovsky, Mishnyakov, Terziev, and Zagraev, and Zarembo. And also, I will briefly mention work in progress together with Frank Coronado, who is over there, and Costa Zarembo. And I also should mention that, so this is about, my talk is mainly about some specific theory, n=4 super mills on the Coulomb branch, but there are some, I also mentioned some properties of, which might apply to general, a spontaneously broken, conformal field theory with moduli space of vacua in which, conformal symmetry is spontaneously broken, and that was also discussed in a series of papers by Gabriel and Leonardo and others recently. Okay, so let's start. So yesterday we had a nice talk by Joel in which he introduced nice results about n=4 super mills. So the important thing is that n=4 super mills is interacting four-dimensional gauge theory, but still in the large n limit, you can compute many quantities using integrability. So in that sense, it is kind of solvable by integrability. But of course, we must admit that this theory, as it is very far from a series of QCD that we care about. First of all, this theory is conformal, and which means that there is no mass gap. And because of that, the natural quantity that we can study here are more like a correlation function of local operators, and there is no no asymptotic state that you can define. And let alone excitation that would resemble mesons or quarks or baryons. And however, the point one of the points of this work, or the reason why we are interested in the Coulomb branch, is that there is a kind of simple way of making this theory a little bit closer to what we care about, like QCD, which is to just give a vev to one of the scalar field. Let's say, so n=4 super mills has 6 scalars, all of which are adjoint, and you can imagine giving a vev to one of them. And this is allowed because n=4 super mills has a flat direction. So as long as you move your theory in the flat direction, this is still a vacuum. And in particular, in this talk, I'm going to talk about some particular way of giving a vev in which you just give a vev to one component of n times n matrices. So this is a SYM theory, and this is adjoint, so this is n times n matrices, and the other ones are 0. So by giving a vev, as you would naturally expect, the symmetry of UN gauge symmetry gets kicked into UN-1, and also, initially we had a superconformal symmetry of n=4 super mills, which is PSU 2/4. That gets broken because, of course, if you give a vev, this configuration is not invariant under the dilatation because the vev itself transforms under the dilatation. And however, the nice thing about this way of giving a vev is that it still preserves all the supersymmetry. So this is all supers. Whereas there is of course, no superconformal. So there is no superconformal, but it preserves all the supersymmetry. And in particular, of course, it also preserves the translation.
So in the D3 brain language, it's just separating a single...
Yes, exactly. I'm going to mention that on this blackboard. Yes, and so now, if you give a vev, then you can study the fluctuation of the theory around this background. And if you study that, and let's say you study the fluctuation of some scalar field around this background by expressing this of phi of j initial field into the web plus fluctuation, then you see that, okay, again, you have n times n matrices, and this component, and then this component, so this is 1, 1 component, and n minus 1 times n minus 1 component remains massless. So this one also remains massless. Whereas this part, which lives on the off-diagonal component, becomes massive. And that is simply because n equals 4 super males has this kind of commutator square potential. So if you have a vev to one of the scalars, then this off-diagonal component becomes massive scalar. Okay? And one important thing to mention is that this off-diagonal component becomes massive for all j, for all value, all 6 scalars, which is not necessarily obvious from this structure, because if you take I equal j, it seems like there is no commutator, so you don't seem to generate a mass term. But there actually well, this also depends on how you do the computation, but there is one particular nice gauge choice, and if you take that gauge choice, because of the gauge fixing term, I equal j term also gets mass for the off-diagonal component.
Isn't it just part of the massive W boson?
Right.
In what sense is it a...
Yes, so it's a part of the W boson, and then in this, and then as Igor already anticipated, so in the holographic picture, what's happening is that we have a stack of n minus 1 brane, which is, and then you have these 3 branes separated from n minus 1 brane by giving a vev, and using the holography, this gets mapped to basically following picture, so this is z equals 0, the boundary of ADS, and then there is some additional, the probe brane, which corresponds to this single D brane. And as Ophar mentioned, this off-diagonal part is basically like a string connecting this 1 brane and then the rest of the n minus 1 brane. And in this picture, and then what happens is that, so they are so these are basically like a W boson. And in the holographic picture, these W boson basically form a bound state and then becomes an open string living on this probe brane. Okay, so this is the bound state of W bosons. And so because of this, in this theory, so this looks a bit like a meson, right? There is something that transforms as a fundamental representation of the remaining un minus 1 or anti-fundamental representation of the remaining u.
This bound state is Coulomb or is Coulombic state? What kind of bounded? Because coupling is small, right?
The coupling you can tune, but okay, so let me just say one thing. So people also kind of analyze the spectrum of these bound states. Yeah. And at weak coupling, actually there is no a bound state, but as you increase the coupling, you start having more and more bound states. So exactly, so what you said is exactly right. Okay. And this is also a nice setup. So for studying various interesting questions about quantum field theory with a mass scale. So let me explain why. So there I was mainly talking about basically the scattering states, asymptotic states, which are made out of a bound state of the W bosons. But it is also interesting to study correlation functions in this theory, in this Coulomb branch functions. So in the case of conformal field theory, if you are not spontaneously breaking the conformal symmetry, of course, people know that 1-point function of some local operator must be 0. However, if you give a VEV, so that's because like a operator normally transform non-trivially under the dilatation, and if the vacuum is invariant under the dilatation, then giving some VEV to the operator is inconsistent with the symmetry. But since we already spontaneously broke the conformal symmetry and the dilatation, like operators actually can, in general, have a non-trivial vacuum expectation value. And that's through the basically dimensional analysis, it behaves like some C number times V times delta O, where V is the like basically vacuum expectation value of the scalar field, which sets the mass scale, and then delta O is the conformal dimension of this operator O. And furthermore, what's even more interesting is to study the two-point function. And now this two-point function is given by V to delta 1 or 1, V to delta O2. So this takes care of the scaling of these operators. And the rest is some non-trivial function of V times x12. So this dimensionless combination, okay? And in general, this dimensionless combination has it contains a very rich set of information. And for example, if you consider the short distance limit, then you expect that, okay, let's see. So let's take this one and then try to expand in the short distance. And in the short distance, which means that x12, V is small, you can study this object using the operator product expansion, much like what people do also in the context of QCD. And so we have some three-point function, structure constant, and then x12 to, so delta 3 minus delta 1 minus delta 2 times operator 3. So you can express it as an infinite sum of the operator. And on the other hand, if you, maybe this is too low for people sitting at the back. On the other hand, if you do the expansion at long distance, you will discover basically all the states, like asymptotic states, scattering states in the theory. And so if you do the long distance expansion, which basically means that this is very large, the leading one is given by some exchange of lightest particle. And in this theory, the lightest particle is dilaton, because like you broke the conformal symmetry, so there's a Goldstone boson. And because the Goldstone boson, because it's an exchange of Goldstone boson, which is related to the symmetry, actually the leading power is completely fixed. Well, not completely, but like a structure is fixed by the symmetry, and it's given by, so there is some Ward identity which allows you to express the leading long distance behavior in terms of this expression. So it's given proportional to delta 1 and the delta 2 of the operator, and the power is 1 over x12 squared. So this is just coming from the fact you are exchanging massless particle, which is dilaton. And then this f pi is the unfixed constant, which is related to some the form factor of the stress tensor.
Doesn't it depend also on the SO6 representation?
Yes, so right, so that's a very good point. So this is a generic structure in the generically spontaneously broken conformal theory. But here, because we also broke, I didn't emphasize it, but we also broke some SO6 symmetry, R symmetry. So there is a kind of also SO6 R symmetry operator. Sorry, R symmetry dilaton, sorry, not dilaton. R symmetry Goldstone boson. So this actually gets modified into something like this. So this is basically Ri1 is a kind of like R symmetry generator acting on operator 1, and Ri2 is R symmetry operator acting on operator 2. And importantly, the coefficient is given by 1, and that is fixed by the supersymmetry. And so this is a leading term, and then of course like there are subleading term, some of which goes like e to minus m and x1, 2, coming from the exchange of massive states. Okay. And
Don't you also have powers that come from the exchange of the UN
right, exactly. So
or UN minus 1?
right. So in general, of course, like for example, there can, let me think. So it depends on, okay, so here I had in mind like a leading large and connected component, sorry, leading large and connected answer, and then I think at finite coupling, in general, there is a gap in this one particle state, and then that's why like it's exponentially suppressed.
But if you're in weak coupling regime, you still have dilaton there, right?
Yeah, the dilaton is always there. Yes.
But there are more power corrections from the dilaton. That's not the only one.
Right. So like especially okay. So if it's not large n, of course there are like two particle states of dilaton, which gives more power correction. That is certainly true. Is that what you meant, or something more?
I don't see how large n changes the answer. There is a cubic interaction of the dilaton. There are quartic and cubic interactions of the dilaton. They are not suppressed by 1/n.
You mean like the?
They're coming from the change in. Oh, I see.
Yeah, that actually is suppressed by 1/n, I think. Yeah.
Yeah.
Okay. All right. So then like there are a couple of questions one can ask at this moment. So the first question is that here, well, maybe the zeroth order question. But let me just write as a result the punchline of our work instead of writing them as questions. So the first thing, which is actually easy to see, but like it's an important point, is that this one-point function of operator O is finite without extra renormalization. It's kind of obvious probably for people who know the subject, but well, I will soon explain why this might be slightly non-trivial, because that's not true if you just start from like a free scalar and then mass deform. So this is true because we are like spontaneously breaking conformal symmetry. And the second property is that it seems, we don't have a rigorous proof, but it seems the radius of convergence of OPE that we use over there is infinite. So this is also probably surprising, especially like I think in generic massive quantum field theory, we probably expect that like it's like OP is only asymptotic and it's not a convergent series. But here it seems like the radius of convergence is infinite. And the third result.
This is a large n, or this is supposed to be also a finite?
Okay, so the result we have is the explicit check in the large n. But there are a little bit more general argument in like Adler and then Gabriel's paper. Okay, and then the third thing is that you can compute this expectation value can be computed by integrability. And then there is a further fourth point, but I don't think I have time to explain, but there is some connection to large charge limit. Okay, yes, I don't have time. All right, so let's quickly go explain the first point. So the finiteness. So to appreciate why this is slightly non-trivial, let's take the case, let's consider the case in which this is not true, like a free massless boson. Start from the free massless boson, and then do the mass deformation. And then let's take some operator which is well defined, like it's phi square, in the massless boson limit, which is defined by basically taking the limit of 2-point function, phi x and phi y, and then just basically removing the propagator connecting x and y. So this is just a normal ordering. So now let's try to evaluate this using the, after doing the mass deformation. Because everything is free, so you can actually do it very quickly. And the answer is, after the mass deformation, is of course simply the difference between the massive propagator minus massless propagator, which in the momentum space, which is very simple, ddk to pi d e to ik x minus y times 1 over k squared plus m squared minus 1 over k squared. Okay? And then clearly you can see that at d equal 4, this is logarithmically divergent. Therefore, you basically need to do extra renormalization in order to have a finite one-point function. However, I claim that this is not the case in the theory with spontaneously broken conformal symmetry, and that is because, so in a spontaneously broken CFT, and one very abstract argument is that when you have a spontaneously broken symmetry, a conformal field theory, and you go to the vacuum moduli, what you are doing is that evaluating some operator in some non-trivial state, but you are not really changing the theory. So this is like a state, vacuum state. In moduli. So, but you are not changing the theory, so that's why things should be well defined. But okay, this is rather abstract. But if you have some Lagrangian description, you can actually also argue more explicitly. So when you do that, have Lagrangian description, there are like several ways to perform the renormalization. But one way of doing the renormalization is that so what's the, I don't know what's the best name, but like I'm calling it background field renormalization. So this basically requires in the renormalization procedure that correlation functions are finite at arbitrary background of this theory at any background. So this is just like a one typical way background of doing the renormalization. And okay, so this is one way of doing the renormalization, and then the point is that going to the Coulomb branch or giving a wave to scalar field is just some particular case of constant background.
But
So Yep.
But is it possible to say that, look, n equal 4, say, before spontaneous breaking is finite series, right? When it's finite series and then you introduce this vacuum average, then the point only is that, this vacuum average does not give you dependence onto UV cutoff like it was here. Once there is no dependence on UV cutoff, no, I mean, so it means that there is no UV contribution, right? So that's enough to say that it would be still fine.
Probably yes.
Yeah, I think that your argument along this way in certain
Yeah, I guess, yeah, probably it's related indeed, yeah. Right. Thanks for the comment. And yes, so these are kind of like two arguments. And indeed, like one can actually see that by explicit computation that it's finite without any renormalization. Okay, so I'm running out of time, so let me now quickly go to the second point, which is the radius of convergence. So, and I'm going to explain the very explicit computation, the simplest explicit computation, which is basically computing some two-point function of single trace operator at point x and y. And then let's also evaluate the leading connected diagram at tree level, at weak coupling. So that is basically given by this kind of diagram. So you have two operators, and then you connect using the double line notation, you connect them in this way. So here, by red line, I denote that the index here, like a gauge index here, is 1. Whereas here, gauge index j is 1 to n minus 1. So this is a kind of like a leading connected contribution, which of the two-point function, which does not exist in the like a usual conformal point. And each of them is given by the massive propagator, which is this k1 v of x, like a Bessel function that also showed up in Zohar's sock. And the point here is that if you expand k1 of v of x, then it's given by 1 over x times some power series. And then there is also a term which is given by log times power series. Okay, so this log is slightly worrisome because like if they are, it's not something that you normally see in the OPE expansion, convergent OPE expansion, but you can actually see that this log can be kind of absorbed into the anomalous dimension of the local operator, because I probably erased it, but if you have a 2 operator and then write it as like a C1 to 3 times some power, delta 3 minus delta 1 minus delta 2 times expectation value of O3, there is this like a power which depends on the dimension of the operator 3, but this operator 3 can receive some like an anomalous dimension, so this by itself has an expansion in coupling, and then that produces log of x. Okay, so and then once you absorb this into the anomalous dimension, you can actually see that this power series and also this power series has infinite radius of convergence. Okay, I have 1 minute to talk about integrability. So let's talk about integrability. So now, finally, let's talk about integrability. So in this theory, it turns out that you can actually compute one-point function of single trace operator using integrability. So let's consider the operator, which are purely made out of scalar. So in the n equals 4 supermills language, this is often called SO6 sector, subsector of the single trace operator. And at tree level, and then the nice thing about integrability is that you can actually map this computation into the computation of some spin chain. So you can view these indices as some kind of like a spin index, and then view this operator as some state in the spin chain. Okay? So this is SO6 spin chain. And then this 1-point function at tree level is given by you can express this in terms of overlap in certain state, which we call spin chain boundary state, and the state that describes the operator. Whereas like this spin chain boundary state is given by where n is basically denotes the direction of the scalar depth in the SO6 direction. Okay, and these boundaries, and furthermore, you can show that these boundary states are annihilated by infinitely many, like a higher spin the higher charges that exist in this integrable spin chain. So this basically means that this has a very nice property, which is called an integrable boundary state. And in particular, because it's given by integrable boundary state, you can express it in terms of some nice determinant formula where the entries of this matrix is given by what's called rapidity of magnons. So they are basically momenta of some magnonic excitation on this spin chain. And furthermore, you can actually, so this is basically tree-level analysis, but you can promote this computation into the finite coupling computation because by requiring that this boundary state is annihilated by Poincaré Suzy, you can actually fix B uniquely together with what's called boundary and Baxter equation, which exists in the case of integrable boundary state. So this last part was a little bit quick, but so this is basically the overview of this paper. Okay, let me end here.
It's about this convergence.
Mm-hmm.
I was thinking that it's like a question to you, but because I think that the tool which kind of related to convergence is using instanton. So because instanton could give terms which are not picked up by normal operator product expansion. So it means that it could be in your case some special feature of this which kind of connected to convergence. But it is a question.
Okay, I see. So instanton, you mean like a usual 4D instantons? Like,
No,
or
I have
just
in
like,
mind using kind of 4D instanton operator product expansion in 4D, right? But it could be, I mean,
I see.
more generic, right?
Mm-hmm.
And it could be so you probably better know what kind of instanton you can use, but something which gives you deviation from operator product expansion.
Right, yeah. Right, so, okay, so I'm not sure if I'm answering your question, but here, of course, this is a gauge theory, so in principle there can be instantons.
Yeah.
But in the limit, indeed, I was talking about, instantons are invisible because we are in the planar limit.
Yeah, it's okay.
But right.
It's us.
But on the other hand, I think like there are also papers by Adler and Gabriel in which they studied the theory, which is not in the large n limit, and also there, I think they saw that the radius of convergence is infinite. So
I think that it's not compatible. Okay, but maybe.
okay, there we can discuss a bit later.
So you mentioned the bound states of W bosons,
Yep.
but there's also just a single W boson, which is a BPS state, and then excitations on top of that.
Right.
Can those also be computed by integrability?
You mean BPS double boson?
But the excitations on top,
Ah,
which
the
are not
excita-
BPS.
right.
So
Okay, yeah, probably. In particular, like I think if you separate two of those branes out of like a stack of n-2, then like this is also kind of integrable setup, so it should be possible.
Yeah, if you can compute that, extrapolate the strong coupling, you can compare with the ADS-CFT, right?
Right.
I don't know
So
if you've done that yet.
yeah, so we
Just,
did
in the bulk compute. They
right.
found
So
it, right.
right, we did it for the BPS operator because that like a 1-point function in BPS operator is actually protected, so you can just do the computation at tree level and compare with holography, and then those perfectly match.
Any other questions? If not, let's thank Shota again.